All right, let's get right into it. We're talking about an absolute giant of the 19th century, William Thomson, who you probably know better as Lord Kelvin. This guy was basically an architect of modern physics as we know it.
So, you gotta understand, in his day, Kelvin wasn't just some famous scientist. He was pretty much the most famous physicist on the planet. I mean, think of him like the Einstein of the Victorian era. He was this towering figure whose work just defined the entire second half of the 19th century. Yeah, his name is all over the place, right? You've got the Kelvin temperature scale, of course, even parks named after him in Glasgow. But what did he actually do to get that huge reputation?
Well, to put it simply, his entire career was basically him going head-to-head with the biggest, toughest scientific and engineering problems of the century. And he wasn't just dipping his toes in. No, he was diving headfirst into the deep end.
And this is what's so cool about him. Kelvin was this rare hybrid genius. On one hand, you had this brilliant mathematical physicist, just reshaping fundamental theories from the ground up. But on the other hand, he was a master engineer, a practical inventor, who could get his hands dirty and solve real-world problems. That mix, that was his superpower.
Okay, so let's tackle the first big one, the problem of heat. See, in the mid-1800s, the Industrial Revolution is just booming, right? And scientists are wrestling with this massive, fundamental question, what even is energy?
So Kelvin's first huge breakthrough was wrapping his head around the idea of absolute zero. And we're not just talking really, really cold here. No, this is the theoretical point where all molecular motion just stops. Dead. It's a true fundamental limit for the universe, and it doesn't matter what substance you're talking about.
And get this, he didn't just dream it up. He actually calculated its value with stunning accuracy. He built on some other folks' work, sure, but he nailed it down to about minus 273.15 degrees Celsius. All of a sudden, physics had a solid absolute floor to stand on.
And that calculation directly led to his most famous creation, the Kelvin scale. This was a total game changer. Why? Because it wasn't based on some random physical thing, like the freezing point of water. Its 0 point was fundamental, the absolute end of all thermal motion. It was revolutionary. He basically created a universal language for temperature that all of physics could use.
His work on heat didn't stop there. It also led him to lay out one of the cornerstones of physics, the second law of thermodynamics. You know the gist of it, even if you don't know the name. It basically says you can't get something for nothing. And in fact, you can't even break even. Energy always spreads out, it always disperses. And that puts a hard limit on how efficiently we can ever turn heat into useful work. All right, so from the world of abstract physics, let's see how Kelvin applied these exact same principles to a challenge that was anything but abstract, connecting entire continents. We're talking about conquering the Atlantic with instant communication.
Think about this for a second. The goal was to lay a telegraph cable across 2,000 miles of deep, treacherous ocean. The scale of that undertaking back in the 1850s, it was just mind-boggling.
So the first few tries failed, and I mean they failed spectacularly. Nobody could figure out why. Enter Kelvin, the mathematical physicist. He crunched the numbers and came up with his law of squares. It predicted that the signal would get delayed not just a little bit over distance, but by the square of the cable's length. That insight was everything. It finally explained why the signals were turning into a garbled, undetectable mess. And man, what a saga this was. We're talking years of repeated, just heartbreaking failures. One attempt in '57, nope. Another in '58 actually worked for about a month. And then, poof, silence. This was a massive, multi-year, multi-million-dollar gamble against impossible odds.
So what finally cracked the code? You guessed it, Kelvin, this time putting on his master engineer hat. He invented the solution himself. It was called the mirror galvanometer, a device so unbelievably sensitive that it could pick up the faintest, weakest electrical whispers that survived that 2,000-mile journey. It was an absolute masterpiece of technology.
And the impact? It literally changed the world overnight. Suddenly, communication between Europe and North America went from taking weeks by ship to just minutes. The entire planet suddenly felt a whole lot smaller.
But, and this is important, Kelvin wasn't always right. Which brings us to the third huge problem of his day, the problem of time, and more specifically, a raging scientific debate over the age of the Earth itself.
So Kelvin, being Kelvin, used his expert knowledge of thermodynamics to figure this out.
He calculated how long it would take for a molten hot Earth to cool down to the temperature it is today. His answer? Somewhere between 20 and 40 million years. The problem was, this flew directly in the face of what geologists and Darwinists were saying. They needed billions of years for things like evolution and geology to make any sense.
And this caused a huge scientific uproar. I mean, Kelvin's physics was rock solid. His math was perfect. So what in the world was he missing?
It turns out he was missing a piece of the puzzle that nobody in the 19th century even knew existed: radioactivity. See, there was this undiscovered heat source deep inside the Earth, constantly cooking the planet from within, keeping it warm. That's what threw his calculations off. It's a fantastic example that shows it wasn't his logic that was wrong, his data was just incomplete.
And you know, that whole story kind of brings us to his ultimate legacy. Because even though he was wrong about the Earth's age, the way he attacked the problem perfectly captures his core philosophy. You could call it the gospel of measurement.
I mean, his influence is just so massive that his name is attached to an insane number of things. You've got the Kelvin wave, the Kelvin balance, Kelvin-Helmholtz instability, Kelvin functions. Seriously, the list just goes on and on. It really shows you the sheer range of his work.
And check out this number, 650 plus. That's how many scientific papers he published in his lifetime. The man was an absolute machine.
But really, if there's one thing that sums up his entire scientific soul, it's his famous quote of his: "When you can measure what you are speaking about and express it in numbers, you know something about it." For Kelvin, if you couldn't put a number on it, you were just guessing. Measurement was everything. Which kind of leaves us with a fascinating final thought. When you look back at his miscalculation of the Earth's age, was that really a failure of his method, or was it just the inevitable result of working with the limited, incomplete data he had at the time? It's a great question, and I think the answer gets right to the very heart of how science moves forward.